Today we will see the explanations of the effect which we observed yesterday, and if necessary we can still repeat the experiment. Actually, I prepared also a demonstration in which I will change the wavelength of the laser. What you observed yesterday was an effect which is referred to as interference. And let me remind you that if two or more waves pass through the same region, there are certain conditions that the waves can reinforce the oscillations of the fields, or in general, whatever oscillates in this particular region, or in this case we call it constructive interference, or they can also cancel out the oscillations. This is referred to as destructive interference. The simplest arrangement of interference, and actually you probably saw it if you play with a plate with soap bubbles. Also, very often probably you saw a spill of oil on a pavement, and in both cases you could see various colors. That the film produces various colors. These colors are effect of interference in the thin film, and I'm going to talk about I will start the presentation with the interference in a film, because it is easier to understand than the one which we observed yesterday. One thing which we have to realize, what happens actually when a wave is reflected, and what happens with the phase. So if the wave travels in a medium with a lower index of refraction and gets reflected from the higher index of refraction, then the phase is going to change on the reflection. During the reflection, the phase of the wave is going to change by pi, number pi. If it happens that the reflection occurs from the medium with lower index of refraction, there is no change in phase. Now, it is difficult to demonstrate it directly, to see the change of phase on reflection in electromagnetic wave. We can only recognize it by the pattern, interference pattern which it produces. However, on mechanical wave, it is not that difficult to demonstrate. So I'll show you the two cases of reflection on this mechanical model of a wave. So I will do, what you will have to do is actually, I will create a crest on one side, and I want you to observe what happens with the crest after it is reflected from this end, and after the wave is going to be reflected from this end. Yes, so let's start. I will start it this way. Did you see how it was reflected? Let me repeat it again. Oops, I messed it up. So it was reflected from this surface over here. Now I will change actually the medium of this surface by holding the last rod and see what happens now. Oops, hold on. Did you see the difference? Who saw the difference? And can you maybe describe the difference? Lee, did you see the difference? How about you? Well, I don't want you to explain why it happens. It's simply nature of nature. It happens because nature is constructed that way. Right. We recognize that actually in one situation, like in the first situation, after reflection, crest stayed as a crest, because I did not create a sinusoidal wave. I created just one pulse. So look what happens with that pulse. Yeah, after reflection, it is still a crest. Now, if I hold the other end, it turns into a trough. Right now, what's the difference really between crest and trough? And so, for example, if a wave travels through this point, and we stop at the point when at this point we have the crest passing through, which means that we have the highest deviation from equilibrium value. So, for example, for electromagnetic wave, if we consider electric field, when crest passes this point, it means that we will have the highest value of the electric field vector. What is the phase of it? Now recognize that at each point along the wave, the oscillations are harmonic. They are described by a sinusoidal function of time. So what should be the argument of the sine function if we have the highest value? Well, the highest value for sine function is 1. Very good. Right? For what argument sine of the angle is, sine of that argument is equal to 1? How much? Pi over 2. Correct. Right. So when the crest travels, at the crest phase is pi over 2. Right? Now this phase pi over 2 travels together with the wave. Yep. So later on it moves to next point and next point and next point. Now if we had this type of a reflection, on this way we had a phase pi over 2, and after reflection the phase was also pi over 2. So what was the change of phase? 0, correct. However, if I hold this end, now after reflection, crest becomes trough. What is the phase in the trough? 3 pi over 2, correct. Yeah, because now we have to have the sine of that argument to be equal -1. So on the reflection, the phase changed from pi over 2 to 3 pi over 2, which means that the phase changed by number pi. All right, so if we have such a situation, I mean, really, this is repetition of this demonstration, except that let's try to imagine it if we have different media for electromagnetic wave, in which electromagnetic wave, so index of refraction over here is n1, and index of refraction over here is n2, and n2 is greater than n1. So we can think about it that this is air, and this is, for example, a film of oil or glass or whatever. So if the incident wave travels this way, that, well, right now crest is approaching the surface. When it is reflected, crest is going to be reflected. However, if the wave goes further, then it it switches the phase. Am I consistent? Actually, I'm not. Now, over here, it was that crest was approaching, trough is reflected. Here we have the condition for the first one. And in this situation, crest was approaching, and crest is reflected. Now, if we think about, again, about this arrangement, so we have air and air on this side, and let's say a thin film of oil or whatever, the light incident on this film, well, some of it is reflected at this surface, some of this is transmitted and reflected from this surface, and some of this is transmitted further. Now, the one which is reflected back can be again reflected down. I mean, one which is reflected up can be still reflected down, and again at this surface, part of it is transmitted, part of it is reflected, and so on. But if we understand, if we just consider these two and understand what will be the result of those two waves coming away from this object, then we will understand what will happen even if we have a lot of them. Yes, so now we can recognize that in this region we have two waves traveling. One is which was reflected from the front surface, and one which was reflected from the back surface. If that angle is not, if the angle of incidence is close to 0, these waves will, the beams will meet. I mean, and practically we will have two waves traveling through the same region. Now, not only that they are traveling through the same region, but they maintain phase difference. It is that the two waves are dependent. The phase difference between these two light beams is determined by the length of the path which it had to travel and the wavelength of the incident light. And that if it happens that the phase difference is maintained, we say that the two beams are coherent. Coherent beams maintain their phase difference, and only coherent beams really produce interference. Laser is a source of very coherent light. However, sunlight or light bulb, it isn't. It is not. But if I take a relatively close beams or manipulated the light in such a way that the path differences for the two beams are not large, that those will be coherent as well. All right, but for simplicity of analysis over here, let's think that this is a sinusoidal, in other words, monochromatic light approaching this object, and if it is sinusoidal, it will have an infinite coherence. So forever, it will maintain phase difference between the two beams. Let's consider. I mean, the drawing is not exactly at normal incidence, but if I think now about this angle of incidence to be smaller and smaller and smaller, these two rays will overlap more and more. And for such a situation, let's analyze how the two beams are going to interfere. Well, so for a constructive interference, well, we will have to have a condition that the light which goes in, travels in that medium and back meets the one which is reflected straight in the same phase. In other words, in the reflected beam, crest of reflected beam from the first surface has to meet with crest of the reflected beam from the second surface. if crest meets with crest from the two beams, we will have constructive interference in reflection. And let's now think what is the required condition for constructive interference. By the way, if we have constructive interference in reflection, then this beam and this beam, these two beams, will simultaneously interfere destructively. You could even come to that conclusion just from conservation of energy. If we have a lot of radiation energy being reflected, then obviously we cannot have energy being transmitted. And vice versa. If we have destructive interference in reflection, so no light is reflected, then a lot of it has to be transmitted. All right, but let's think just about reflection. Well, if thickness of this film is T, well, the light which, the path which the light is traveling forward and backward is 2 times T. Now, we have to recognize that on the reflection from this surface, this wave changes phase by pi. Well, therefore, the light which travels over here, this distance has to be such a multiple of the wavelength. This way, trough will meet with trough, and crest will meet with crest. So it is a half multiple of the wavelength. If 2 times the thickness of this film coincides with a half multiple of the wavelength, then we will obtain constructive interference. Now, for the destructive interference, well, it has to be that trough meets with crest. So trough from the reflected beam must meet with the crest reflected from the second surface. Well, it would require that the path which the light travels over here, 2 times this which is 2 times this thickness, again 2 times this thickness, must to be equal to the multiple of the wavelength. Maybe I will actually make a drawing of it. Why? That it should be this way. Yeah. So let's say that we freeze a situation that crest of the incident light hits the surface. Well, if crest hits the surface, which means that in the reflected light we will have a trough. Right? Now, in order to have constructive interference, the wave which is reflected from here would also have to have a trough over here. Well, it means actually I marked it that way. Okay. And now let's see. Okay. Did I make it? Yes. Okay, I made it right. Yes, so the incident light do you understand? I mean, I'm not sure if I'm convincing over here, but do you understand the idea? Yeah, it is that let's make it maybe simpler. Let's make that the film is equal half of the wavelength. All right. So if we have yes, so really on the formulas m is equal 0. And I'm trying to show a situation for constructive interference. All right, so reflected light, yeah, if this is, okay, so this is how the light is going to, will be the distribution of, well, electric field in this direction. Now over here, phase doesn't change, so the wave is going to be like, how about if I use a different color for reflected? So black is incident. So this is how the reflected from this surface is going to look like. And with green line, I will draw a wave which is refracted from the front surface. So you see that crest meets with crest. Now let's say that I will make the thickness of the film, I will make the film thicker. Yeah, so this was 1/2 of the wavelength. I have to take 1 wavelength. It's going to work or not? I'm confusing myself. Because I see that actually this should be shorter. It should be like that. Let's skip it. I got confused myself with this one, so think it over. I mean, because it is not that complicated. Just you have to really to think about it. What should be the arrangement that crest meets crest, and for constructive interference, and crest meets trough for destructive interference. And these are the conditions at which it happens. So if we, for example, have a white light falling on the film, white light will contain a lot of wavelengths. Some of the wavelengths now will be such that they satisfy condition for constructive interference. Let's say that red light satisfies this condition. Well, if red light satisfies this condition, green line will actually satisfy the other condition. So in the reflected light, we will be missing green part of the spectrum, and therefore the light reflected won't be white anymore. it will become somewhat purple. In the transmitted light, we will, on the other hand, have constructive interference for the green part of the spectrum. So we will see green light on the other side. Actually, this is a basis for so-called interference filters, which are commonly used in optics to get rid of undesired wavelengths from the spectrum, particularly in a part of science which is called spectroscopy. And if you are a chemist, or if you are a physicist, or even a biologist, you will have to deal with spectroscopy. Raman spectroscopy is probably the most common in all three. So in Raman spectroscopy, which is actually subject of studies in this department and in the department of chemistry again also, we use lasers to perform this experiments in spectroscopy, and this spectroscopy requires that we use really a monochromatic light. Lasers don't necessarily produce a single line, single wavelength. So in order to isolate that single wavelength which we want to use, we very often use interference filters to obtain this effect. All right, let's now take a look at interference in another situation, and I want to go to discuss actually interference in two situations. One is that we have two slits very close to each other, two thin slits very close to each other, and the other one will be a single slit. A single slit will also produce interference pattern. Well, Huygens actually, this is how you spell the name, came with a theoretical, I mean, pretty good justification how actually to analyze the process of interference. He noticed that actually if a wave passes through a certain point, this point can be considered as a source of a secondary wave which has a spherical symmetry. Now, this secondary wave is referred to as wavelet. So let's say that we have a certain wave, and for simplicity I picked a flat wave. These lines, let's say, represent crests. And the fact that it is plane, it means that the wave is plane, means that the points which have the same phase, like all of them have, through all of them a crest is passing, will form a plane. Now, each point along this line is a source of a wavelet. So I can consider that from this point there is a spherical wave coming out, and from this one there is a spherical wave coming out, and from this one there is a spherical wave coming out, and from this one, and actually with all points in between. Well, so those wavelets actually will create still a plane wavelet. Now, if I think about a wave which is coming from the point, I can also consider it now that each of those points is a source of a wavelet. And again, if I think about how those wavelets propagate, the superposition of the wavelets will again reconstruct that cylindrical or circular shape of the wave. Well, we will use Huygens principle to analyze what will happen if we have an obstacle on the path of the wave which has two slits. And for simplicity, first let's think that these slits are infinitely thin. So if I have a wave coming out from the left-hand side, each of those slits now will become a source of a wavelet. However, those parts which are obstructed will not produce any wavelets. So this slit will produce a spherical or circular wave coming out that way. I mean, it's coming out from this point. And it propagates in all directions from that slit. From the second slit, we have the same situation. Light propagates in all directions. Now, let's take a look at various directions over here. Actually, probably first will be better without that. Look at this line over here. Along this line, consider that these lines represent crests, because really they are lines of the same phase. So for simplicity, we can think that these are crests. So here we have crest, here we have crest. It means that over there is trough. Here's trough, crest, trough. Do you understand that? All right. So along this line, compare the phases of the two wavelets coming out from the two slits. They meet. Does crest meet crest or crest meet trough along this line? I'm talking about line like this. Look at this point. At this point, what met what? Crest met crest, correct. Over here also, crest met crest. Along this line, crest met crest. But it's not the only one. Look at this point, this, and this. Here I have another line that also crest met crest. And another line over here. I can find, however, points where crest met with a trough. For example, at this point, at this point, at this point. So actually, I mean, here we had constructive interference. In between, we will have destructive interference. So now, if I place a screen, I will get places where the two waves reinforce themselves and result in constructive interference and produce a bright spot. And there are regions where they interfere destructively, and well, we won't see anything over there. Let's now find the conditions for constructive and destructive interference. Well, for constructive interference, crest, I mean, if I consider, let's say, this, or how about this point? In order to have constructive interference, it means that crest has to meet with crest. Well, which means, and also here. Well, it requires that the path difference from one slit and the other slit is a multiple of the wavelength. I hope that I will be able to draw that. So let's say that we have those two slits, and in order to have constructive interference here, let's make it here, at this point. And so at this point, it's like we have crest, So if I consider from this point, we also have to have crest. This way we will get constructive interference. Now, here is a situation that I picked a point that the distances are equal, right? So it is almost obvious that crest will meet crest. However, I can find another point somewhere over here, so that three wavelengths, it will be three wavelengths from this slit, but four wavelengths from that slit. Over there also we will have the same constructive interference. Because, I mean, look at this point and count how many crests we have from each slit. So let's start that this one is 0. So it will be 1, 2, 3, 4, 5, 6. Now from that one, this will be 1, 2, 3, 4, 5, 6, 7. Yeah, one wavelength further. So at this point, crest will also meet crest. All right, now let's see at what angles actually we will get constructive interference and destructive interference. The path difference between the two, I mean, I'm considering now this direction. So here is a kind of a wave front of the wave traveling in this direction. So the phase difference between wavelet coming out from this slit and from this slit is approximately equal to this distance here. Now, if this, if we are considering, oh, it's for that one. If we are considering this line, that this line makes angle theta with that line of symmetry, that this angle in the triangle is also going to be theta, which means that the phase difference is related to separation between the slits multiplied by the sine of that angle here. Yeah, here we have a right triangle. And in order to have constructive interference, this distance has to be approximately a multiple of the wavelength. So here we got a condition for constructive interference in the double slit experiment. Well, for destructive interference, well, of course, it has to be in between. So crest now has to meet a trough. Therefore, if we have if this distance here is increased by half of the wavelength, this will satisfy that condition. Now we can actually analyze precisely what will be the distribution of intensity using phasors. And well, so let's think about electric field produced by this point, by complex electric field produced at this point due to wave coming out from the two slits. So from slit 1, this is the form of the complex electric field at this point, and this is complex electric field from the other point. Well, if I draw the phasors, the two phasors differ with the phase. So here is phasor representing electric field produced by one wave, and here is phasor of the electric field produced by the other wave. The resultant field is the sum of those two fields. So I had to add those two phasors. Now let's mark that this angle is phi, and by phi I will understand the difference in phases between the two phasors. And actually, if I look at these numbers over here, I recognize that phase difference comes from the fact that this term is different than this term. The difference between these two terms actually gives me the phase difference between the two phasors. Okay, and now I can recognize that over here I have difference in the distances from one slit and another slit. So I repeat it again that it's really separation between the two slits multiplied by the sine of the angle at which we observe the light. Well, resultant electric field, in order to get resultant electric field, I will have to add those two. So if I add them, I mean, this is just an algebraic expression. I copied E0 from here. I copied e to I omega t. Should be with minus, though. And then I have the remaining part. Okay, so it is now, I substituted this difference over here and got the expression for a complex electric field. It's this complex electric field. Now, in order to see intensity, I can recognize that intensity, I mean, we had it, that intensity of the light is speed of light multiplied by the average density of the wave. And average density is proportional to square of the electric field strength. So in other words, I have to take from this complex electric field, I have to extract the magnitude of it. And, well, so it is, I copied C, and magnitude of a complex number is complex number times its complex conjugate. Now you can recognize that I have 1/2 permittivity of free space, because this is what we had in the relationship between the electric field vector and the energy density. And this entire expression now represents square of the electric field strength based on this complex number. The rest is actually algebra. However, it's a complex algebra. So I'm simplifying this, and since I have a little time, I don't. You can go on your own to analyze the steps. What I want you to get that in the summary, I can simplify this expression to such a function of position from the center point or from the point of symmetry. And so I have a cosine function, and the argument now is the distance from here. Well, if I plot it, I mean, really I have a square of cosine function over here. So this analysis will lead to a cosine square dependence of intensity. And this is really the pattern which we observe. I want to skip Lloyd mirror. How about if we come back to this later? Now, I won't be here tomorrow. Professor Leibsley is going to continue the lecture. And we have the test on Monday, right? Okay. So let's end the class at this point.